Okay. Maybe let me write the exponential that we already did. This is having power series that is x with power of n and n factorial. Okay. Another way to make up the formulation, if you think that you need another approach, to take some time to prove that this e to the x is equal to this power series. So if we remember, if we are going back to the calculus 1, if we have e to the x, if I take the derivative, this will be still e to the x, right? And that's the definition of e. So the function e is when we derive them, it is still the original function. Or we can also say the property of e is when we derive, this is actually the same thing as its derivative, right? Okay. Now, to make some logical sense in how we can get the series, okay, we can take some time to look on this relation. Okay, the functions is equal to its derivative. So e to the x, we derive e to the n. Right? Now, let's just assume that we start with y. Let's just assume start from 1. Okay. But based on what we did here, this should be equal 1. Okay. This is just like a playing some games. Okay. So this is 1, 1, but it seems it's not really correct. In a logical sense, if you want to have this 1, 1, we need to plus x, right? If we derive that, it becomes 0. Okay, so let's plus x. But then we keep going on. We need to take it into the equations that y is equal to dy of dx. So maybe we can plus x here. Let me use different color. And again, it seems that we need to add more from here to make it equal. Okay, so let's try to do that. So plus, we have to have something x squared here, but in order to become x, we need to divide by 2. Okay. So then we derive this and become x, but then we need to have this again equal. Okay. Okay. And then we need to have something here that when we derive, it becomes this. Okay? And we add more. So if we derive, we need to have 3, and we need to divide by also cancel 3, right? Okay. But we need to have this sequence here, this x to the power of 3 need to become this half, right? So we need to divide by 3, divide by 2. Okay. But then we need to have also the same thing here. And you keep going and going, and when you realize this formula here is the same formula as our series. Okay? It's 2 factorial, 3 factorial, 4 factorial. And if you keep going and going, this is true that this is our definition of E. Or we may write as our series formula. Okay. So this is something that you can also think. Okay. So we can think the relations between the function and its derivatives for E, they always have the same value. So we can also get this series, sequential series. Okay, now still E. The question is now, if we can, for example, represent all the functions in the 11.9 section as a Maclaurin series, then how we can determine that this E has the power series? So the question is how Or question can be also understood as how we can know the series, how we can know exactly the series having the, or the function having the power series. Which means that we need to look at more into approximations. Okay? So we need to have some visuals on the functions, and when we take some limit, and we take sometimes to take the sum of the series, we will look on the error that they will make. Okay? So this is what we are going to do. So we will look for what circumstance is the function is equal to the sum of its Taylor series. Or let me write, if a function has derivatives of all orders, when the function itself we can write as, this is the coefficient if you remember, and then n factorial, and then x minus a, as in the general power series formula. And then if you think on how the series become converge, okay, that means the functions is the limit of a sequence of partial sum. Let's say the partial sum is Tn, where Tn is partial sum. Partial sum of the Taylor series And then we define the partial sum, the Tn, or if you expand from the integer equals 0, as in powers series, or in the Taylor series in this case. So when we define this as a partial sum, then we will define an exact value. So while we are doing this, okay, remember, if we discuss about series, there are two exact points that we are talking. The first one is the sequence itself of the and the second one is the sequence of the partial sums. Why we are need those 2 points? Because the partial sums, basically they will limit our calculation. So we are going to have more converged solutions. Okay. So this is what we are going to do. So we are going to have some approximation. So we can try from T1, T2, T3, which means if we are going to have the E, we are going to have some sum at S1, S2, like we did before, actually the same. But this is on the Taylor series. So that's the thing, this T. This is similar to what we did before, like the S. It is pretty similar. But the way we are going to expand the series is going to be the Taylor series. Okay, the Taylor series. And if we look on more details on the Taylor series is actually a polynomial, right? Okay, Taylor series is actually a polynomial. So Tn is basically some nth degree of polynomials. Or maybe Taylor polynomial. Of the function f at a. Okay. So if we have the functions start with when we deal with the e to the x, okay, then our t1, so start from 0 and then 1, so 1 plus x, okay, and then start from maybe 2, this will be 1 plus x squared over 2 factorial. And then start for T3, we have 1 plus x squared, and then plus x cubed, 3 factorial. Okay, now, if we want, we can try to take some time to draw the graph. This is, I think, is a straight line. This is a quadratic, and those are at the cube. Okay. But we observe on certain conditions. So let me just copy my graph. No, this one. Okay. Okay, wait. Now, if we increase our t, so we can try t1, t2, t2 having an even function because quadratic, t3 is cube, the blue one, cube, and then our functions that we want to approximate is t. Okay. You can try as many as tn if you want, okay, but I think we can see clearly from this graph that all these functions, or all this t, or this sum, they will approach this e to the x. Okay. Now we can write from this t, from the graph of t, that the functions is actually the limit as n going to infinity of the t. And then, because its limit, remember, because its limit, it's not the exact same or exact. We cannot say that functions, the value of the function is the same as the value of the tn, because we are dealing with approximation using limit, right? So the exact one, we have still a small error. Okay, that's the actual truth. So when we deal with this T1, T2, T3, and maybe we have T100 probably. T100. It's still not yet as close as to the e to the x. Okay? There will be still a small gap. Okay? Now, that is what we call the error. Or, if we remember the last part, it's called the remainder. Okay, the remainder. Okay. So then we can develop that we have this remainder, which is the difference between the functions and the t. We call the R and X as a remainder of this series, or to be precise, the Taylor series of this particular series. And then we can also write the functions as the t functions plus the remainder. Then, if we can show that the limit when we increase the n of the R and X, if this is going to be 0, then we can write, maybe I need to write down a little bit to the here. Let me move a little bit here. Then the limit or maybe let me write here. It's the same as f of x minus limit, and it's equal f of x. And then it will brings us to the theorem for the Taylor series. That is, if we can prove that the remainder, the limit of the remainder is becoming 0, then the limit of the partial t is equal to the function. Okay. So that means what we did before, or what we did in the Maclaurin series or in the Taylor series, that's all true. Okay, that's all true. So when we have, and we can prove that the limit of the remainder can get 0, then the following limit here is equal to the function. Okay. And to show this limit remainder of 0, we need to have other theorem. Okay, but later on I will show you. Okay, now let me just make some conclusions here. I think I just copy the copy this. Okay, this is what we did before. Okay, so the first one, the theorem number 8 here. If the functions c plus remainder, where t is the polynomial of the function of a, and if the limit of the remainder is equal to 0, then for this radius, then the function is equal to the sum of its Taylor series on the interval of this, of the radius also. Okay. And then to prove that the limit of remainder is true, that it's 0, we need to have some, we call this the Taylor's inequality. Okay, the Taylor's inequality. So we need to set up some component here, that is the f n plus 1 x, or this is actually, we can get this form from the coefficient that we got in the Taylor series, right? And we set up for some m is some random m for constant, and then set up our ratio or radius, okay? And then the remainder will be satisfy these equations. This is actually coming from what we did in the first part, where we need to have the n plus 1 and then n factorial, like we did in the finding the coefficient. Okay, so to make this true, then first we assume that the Fn is less equal m. And then we take n equal 1. Okay, so and in particular we have this. We can set up this for the interval of from a to a plus some d. Okay. Oh, it should be not n. We can just take some second derivative. And then we can set up the integrations from a to x of the second derivative. And this will be equal with this m. And by fundamental of calculus, we can set up the f prime x minus f prime a. So we take the, and then this will be x minus a. And we can rewrite this and make it into f prime x less equal f prime a plus m x minus a. And then similarly, we can take the integral for f prime t. So let's take into some t. And doing exactly the same using fundamental theorem of calculus.
I will take this into dt. And then using the fundamental of theorem of calculus, we will get this plus m okay. And we set up these equations. And then this will be our inequality. And remember that if we set up some reminder, let me write a reminder here, that this is this difference between the functions and t1x. Okay, so reminder 1, this is r1. Okay, so this will be equal with f of x minus f prime a x minus a. Okay, so r1x is less equal and if our f double prime x is greater than negative m, because we take the absolute value, so we take the -1, we will have the remainder, or reminder 1, will be greater or equal with -m/2 x minus a squared. Okay, and thus we can take these two conclusions as so thus from this calculation, what we did here, we then prove that if that the remainder is the difference of the functions and the t of the partial sum, then from what we have here, that the f of x minus this f prime a, so if we have this as our r, then our r should be going to have this particular form, and that is proven to be true into our if you remember the Taylor series of the E, if we have this form, or the Taylor series in the general, we will have this form, and if we take some time to maybe taking into the third derivative, this is just a second derivative and the first derivative, and we look at how we can get the form. We will get the m over 2x minus a squared, and we take maybe from the third derivative, probably we will get m over 6, and then this will be the power of 3 or cube. And this is from the key is that we are only looking on n equal 1. You can go for maybe n equal 2 or n equal 3, and maybe it's taking some time and taking more steps. So for n equal 1, we are going from the second derivative. So if you take maybe n equal 2, maybe you take more derivatives also, and as you increase the n, you take more derivatives and here, and maybe you take some times, and maybe much more longer. You have like longer sequential for the Taylor series. And what it's for is to take some time to prove that your remainder will be in the form of the last part on your equations. So that is going to prove that whether it's true or not. But anyway, I think the more general terms that you need to take as your essential is this: that your functions should have some remainder, okay? And by definition, those remainder as a limit should go to be 0. Okay? Which means what we did in the series that we can represent as a function is basically taking limits. So in every part in calculus, from the first time you learn calculus from calculus 1, you will learn the derivative, the integrations. The connection for all of the calculus is based on the limit. So we essentially use the limit to make all the things seem logical. Okay? So when we take sometimes to make it like 0.000 something, it's still a number, but we take that number because we take the Toll's limit, we take that number as 0. Okay? We take that number as 0. Like you learn how to define the tangent line, okay? And it takes some time, and then with the limit, that's going to be 0. And all the parts from the derivative and integrations, all the things in calculus will be connected with the limit, okay? The limit. And also we see in the sequence and series, when we deal as a functions, then we need to take the limit as a concept to make the representations seems logical. Okay, so that's some time to think about. Okay, now the next section. Okay, I think we already did the sine x. And also for sine x, we can also take some time if you want to prove the Taylor, the partial Taylor, we can do as well. And I think it's much more logical, because if we look on the sine, there will be only two conditions, sine and cosine, right? The derivative or the negative part of it. Okay. So I think it's not really that important. Okay, I think I will give you just summary, some important functions that we might encounter, okay, and some. I think one will be just skip one series. Okay, here's some important Maclaurin series. Okay. So you should be having one more here. It should be not binomial series, but I will just skip this binomial because I don't think it will be much more related. But I think the other one is important. So from the 1 over y minus x, we already did that in the previous sections. Okay, we have e to the x. We also have the sine x, and if you see the pattern here, I think it depends on you which way you are prefer to see the functions. Okay, we should the expansion or just the power series, okay? Or you can develop
by your own. I think that's also true. You can just take some time to expand the Taylor series, and then take a equals 0. Okay, take a equals 0. And the cosine x, when you see the sine x and cosine x, you will see the difference between these two. This is start from x and then x cubed, find the odd power. Cosine start from 1 minus the even number. Okay. And you'll see the tangent inverse is actually similar to sine, but the difference is it's not having any factorials. So actually, you will see some pattern in this some functions here. And ln1 plus x. This is similar to the e to the x, okay? But the difference is, of course, we have 1 in the e and x in the ln. But since it's 1 plus x, it should have the alternate series. Because the default is 1 minus x for all possibilities. Okay. And how to find the radius, you can figure out from the ratio test if you would like, from this series.
So there are a few sections more on the Taylor and Maclaurin. And then we will have more sections on the application of Taylor polynomials, and we will learn more about the error, the remainder.
So
the next one is, we call that the new Taylor series from the old. Which means,
okay, we need to make a new series from the old series. The old series, usually we are going to refer to the above functions.
okay, so this one.
So if we can take some time to modify this functions, okay, we can take this series and make it into a new one. Okay.
So for example, if the functions is x cosine x, then this is just multiplications of x, and then we take the cosine x as our series. So then this is just multiplication with the x, so just take x and then plus 1. Okay. Okay, that's an easy example. Okay, we just multiply x and then try to get into the old Taylor series.
So if you have like maybe encounter this kind of question, you can directly take the cosine x to this series. Okay. No need to prove whether this is true or not. Okay. If you know that the cosine x is this series, then you can just exchange. Unless the question is asking to prove, then you need to prove. But if the question is just asking, please write the function as a power series, then You can exchange cosine into power series directly.
And the other functions, for example, ln 1 plus 3x squared.
So either we multiply or we divide, okay, or we exchange the x. Like this from the ln plus x. So we can just exchange the series in the x with the 3x squared.
Okay. So we can exchange that as in n equal 1. And then exchange x with 3x squared with power of n divided by n. Or if you want to write more precise, okay.
Another question that might be asked is not only to define the functions to the series, but maybe from some series to a function.
So probably if we have the series and factorial. So the question is what is the functions?
And the key to solve both of this question is you need to think several functions that is stated on the reference, like from the 1 over 1 minus x, ln 1 plus x, and then the cos, sine, tangent inverse, e to the x. Write all possibility and make it into our solutions. Okay? So whether it is maybe sometimes it can be from two series combined together, or maybe one series and then you modify the series, and then we can find, oh, this is actually refer to what functions. So that's the key. I think for the first example, it's not too difficult to imagine. This is just to take some multiplications, some modification of x, and some modifications to exchange the x in the power series. The second one, however, we need to think reverse. Okay? We need to think backwards from the series and then make it out to the function. Okay?
So first, probably we can think or maybe write this series as or maybe let's combine this -1 into 2. And -2x with power of n.
I think this is true for this one, right? And then if we remember that we have some variable x with power of n and factorial, which if we remember clearly, this is e to the x, right? So probably that is our solution. So e to the x with the x is exchanged with the -2x.
So this will be equal that this is equal to, or if you want to write more precise, we can write down the e to the x first, that this is equal to this power series. And then we can provide that this is true, that when we have this, then this will be e with -2x. So the functions is e to -2x. Okay, another example, or maybe later one, we will have some short break. Okay, let's continue a little bit. Okay, another example. Another example is if you would like to find the sum of the series is already fixed in numbers. Then first, we can observe how the patterns looks like. So it has at least 1, 2, 3, 4, and then 2 with power of 1, and then 2 power of 2, 2 power of 3. So probably this has something to do with the 1 over n, and then 2 with power of n. So first, we can try to write up the sum. And then we know that this will be half of n and then over n. And if we remember that this particular form is similar to what we have in the ln 1 plus x. Okay. So if we write down the ln 1 plus x, this will be this, right? And so our solutions is we can write down this 1 over n, 2 from n, that this will be similar to ln 1 plus half, in which we can figure it out as ln 3 over 2. Okay. So this is also other way to use the old Maclaurin series to modify the series, or to exchange the series. Okay. Okay, another example. Let me just write first. Evaluate the limit as x approaches 0 of e to the x minus 1 minus x divided by x squared.
I think I'm suggesting to familiarize with the Maclaurin series. That is the essential function. 1 over 1 minus x, ln 1 plus x, e to the x, sine x, cosine x, tangent inverse x. Those functions. Okay, then if we need to evaluate this limit, okay, I think if you remember what we did in calculus 1, if we check the 0 inside, if we put 0, then this is 0 over 0 situation. This is indeterminate form. We can use Hopital rule, right? We can I think derive twice, and then we can have the answer directly. And I think that's really fast. Right? But since we already learned how to take our functions as the power series, or we can expand this e to the x into some expansion, we can also do that and try to solve this limit using those expansions.
Okay, so if we remember that if we have e to the x, then this will be 1 plus x squared plus x cubed, or maybe let me write 1 factorial. Okay, so let's try to take this into our e for this limit. So let me change the e with the 1 plus x. And then minus 1 minus x. And divide all with x squared.
And then we can see that this x will be cancelled with this minus x, okay? And this 1 also cancel with negative 1, right? So we can cancel the
First two terms.
and then we can divide by x squared. So we can exchange x squared, cancel this, and all the terms will be minus 2 for the x.
So we will have, this is cancelled, and also cancelled for all of these terms. So we will have limit of x approaching 0, that it starts from 1, 2 factorial, plus x, 3 factorial, plus x squared, 4 factorial, plus dot, 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 dot.
And clearly from here, we see that when x is going to be 0, this part will be 0, and this is going to be half.
Which is clearly the answer. Okay.
If you derive twice using L'Hopital rule, the answer also half, right? E to the x, this is 2x, and 2x, and then 2, e to the x twice, and e with power of 0 is 1, so 1 over 2, right? Okay. So we can also consider to use this expansions also. So now we have the series expansions as your functions. So whenever you find a function that can be exchanged with the expansion series, you can always exchange that and then try some different things. Of course, I think it's still faster using L'Hopital rule twice and then go rapidly up. But I think in some cases that need more of some expansions, like maybe more complicated than this. Probably we need to do just using this and then just try and then canceling some terms. I think also okay. I think also fine. Okay, next technique is we can multiply and we can divide with each of the power series.
I think it's a little bit complicated for the multiplications, because what we are going to do is we need to multiply and maybe divide the expansion. Okay, so it's going to be a little bit complicated. So the questions, we find the first 3 non-zero terms in Maclaurin series for The first one is e to the x sine x. The second one is the tangent x. Now we have e to the x sine x and tangent x. We can think tangent x sine x over cos x, and we can think on the expansion series, and we can divide those by some long coefficients. This one we can multiply the expansion series of e to the x and sine x. So if we remember that the e to the x will have 1 plus x and sine x will have x, the odd power, right? Okay. So we multiply this. Let me write in more clear. So 1 plus x squared. Let me just calculate the factorial as half, and then plus 1 over 6, and plus dot dot dot. And for sine x, it's x, and then plus, minus, sorry. Let me write minus here, minus 1 over 6. And then plus, dot, dot, dot. And then this is, we are going to multiply. So we are going to multiply 1 to the x, x to the x, all these terms, and also this term. So why we are just looking at this several terms? Because the question is just asking the first 3 terms. If asking maybe more, then maybe we need to have more expansions. So let's try to multiply. Multiply. So this will be x plus x squared plus half x cubed plus, okay, all multiply with x. And the second one we multiply with this negative 1 over 6 for all terms from e to the x. Okay. So let me write below. And then add. So this will be ex sine x is equal x plus x squared plus at least 1 over 3 x cubed. And then plus dot, dot, dot. At least the 3 terms for the ex sine x. So we can also multiply with the expansion. Okay. Okay, lastly, this is multiplications. The other example is the tangent x, which is sine divided by cosine. So which means the expansion series of sine, we have some plus minus. We need to divide by the cosine. Okay. But since we are only consider the first 3 terms, non-zero 3 terms, the first 3 terms, then we can actually using just several terms. So probably we can write down tangent x as a sine x divided by cosine x, and write the expansion terms. So x and this is 1. Let me just write the 3 terms both of sine and cosine, and then we can write the long division. Maybe right here. and then divide. Divide with 1 minus x squared plus x with power of 4. So this is just a normal long decision, but what we define is the expansion. Okay? So it's similar with what we did in the polynomial long divisions, if you remember. But this is, we have, let me just exchange this factorial into a number to make it clear. Okay. So first we can take x. So this will be x minus 1 over 2x cubed and plus x5, 24. We take some time to subtract this. So subtract. This will cancel. This will be plus 1 over 2. So 1 over 2 minus 1 over 6 is 1 over 3. And this will be having 1 over 24 minus, so it should be minus 5 minus 1 minus, so it should be 5 over 120 or 130. And then still we have 1 over 3x cubed. We take some another multiplications to cancel this 1 over 3. So this will be 1 over 3x cubed minus 1 over 6 x5. I think we need to have one more. This will be cancelled. And 1 over 6 minus 1 over 30 is 430 or 2 over 15. But since we need only 3 terms, then this will be plus 2 over 15x5 plus dot dot dot. Then we can write down the tangent x as x plus 1 over 3x cubed plus 2 over 15x5 plus dot 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 dot. Okay, any questions before? Any questions before we continue to the next section? Okay. So by this Taylor and Maclaurin series, actually you can represent function as a series, which means that some of your calculus 1 that we have learned before, we can actually solve some of the problems using this series expansion. Any questions? No? Okay. I think next week I will give you some tasks, okay, some like a homework task. So hopefully I can finish the questions by this week, and next week I can upload or
put the link on the Moodle.
Okay. Okay, let me begin the next sections with the approximations. So 11.11. This is applications of Taylor polynomials. So first is approximation. So suppose function x is equal to the sum of its Taylor series at A. Okay, this is just a definition of a Taylor. And then if, okay, T, this is the sum, okay, the nth partial sum of Taylor series. And we can write this as the sum, maybe using different integer. And we can expand. So we know that the Tn, this will approach the function x as n is going to have larger value. So Tn can approximate the function, which means that the functions is going to have these relations. Okay, if we take observations on the first degree, polynomial, okay, of the partial sum, we will have these relations. And if you look on the terms here, okay, this is the same thing that we learned in the previous semester, that we call this the linearizations. Okay, so this is actually similar, linearization. So if we look on this, the first degree, that is a straight line, right? If we look on the previous example with e to the x, when we have t1, it's just 1 plus x, right? And that is precisely the form of the linear sections in the chapter, I think chapter 3 in last semester, that we have linearizations, right? It's similar. Okay. So So if we increase the n, then it will be the second derivative, or the second degree polynomial. And then if we increase n until 3, this will be the third degree, and so on and so forth. And then this will raise a question, how good is our approximation? How good, maybe how good an approximation? Approximation. How large should we take n? So it depends on what error should we require. Okay. And to answer this, then we can take some time to look on the remainder. That is the gap between the functions and the t.
So the idea behind this approximation is the R. Okay? How good is our error? Okay? How good is our error? How accuracy? How accurate? Is 0.001 good, or maybe you need more 0.0001? Okay? That depends. Right? Depends. I think if you deal with the industry, just traditional industry that manufacture maybe steel or maybe component that is not really that small, and I don't think the accuracy will be much problem. Okay? Compare with if you design some parts for airplane, for example, that will be a different case. The way you look on the error is also different, and usually in some industry or some standards. Okay, some standards. If you're maybe dealing with maybe mechanical engineering or maybe material science, some materials or maybe some equipment or device, they will have, we call it some standards. Some standards. Maybe you heard the AMSE or maybe some standards in product. They will have some standard, and they will have some standard for errors too. What errors they should have. Okay, what errors they should have.
So these approximations, first we deal with this remainder. Second, we deal with the inequality that's having some n plus 1 factorial x minus 1 n plus 1. This is if I think I will going to show you how practical we can see the error. Okay, so let's just try to see some functions. So it's either we find the error, okay, by using some n, or we find the n by using some error. Okay, so that should be the idea. Okay. It's similar to what we have done from previous section, but now the difference is we are going to have our remainder as this f and this t, and all the t and f we will define as a Taylor series. Okay, as a Taylor series.
And later on, we will have some definition for remainder that should have this inequality that satisfies this formula.
Okay, let me go through some functions. Maybe from functions, let's just try the cubic root of x. Okay. So approximate the functions by Taylor polynomial of degree 2 at a equal 8. Polynomial degree 2 means that this is the T2, okay, the T2x. We need to have until the second derivative having the quadratics, right? Okay. But first, maybe we can take some time to check some derivatives. Okay, so this is maybe let me write x as 1/3, and the derivative of it is 1/3. X minus 1 is -2/3, and the second derivative we can have -2/9, x -5/3. And then at a equal 8, then we can check the f8. Okay, this is 2. F prime 8, this is 8, 2, 4, 1/12, right? This is also 2, 32, 16. 16 by 9 is 144. And then from here we can take some for the polynomial degree 2 of the sum. So we can take f8 plus f prime 8, 1 factorial, x minus 8 plus then the desired equations, we can exchange the f8, f prime 8, and f second derivative with the calculation we did. We can take it into 2 plus 1/12 x minus 8 plus, this is 1/144, but this is multiplied by 2, so 1288. Oh, it should be negative. This is negative, so this should be negative. So negative 188. And x minus, okay. So we can write that the functions, that is square root of 3, square root of cubic root of x, is approximating the T2. Okay. Okay, and now if we have following questions, that is asking the accuracy. So let me write the question, the following questions. How accurate this approximation when 7 less equal x less equal 9. So we have some interval, okay, for the x. Okay. Now remember that we have the remainder having inequality okay. So when we have the second degree, the polynomial degree 2, which means that we need to take n here, so we need to have 3 factorials and we have the 3. Okay, so we will have the R2 as m over 3 factorial and x minus 8 cube. And then if you look on this series, okay, this series, it's stated from x minus 8, x minus 8, x minus 8. So when x is less than 8, it will be not alternating, right? It will not alternating because it will be a negative. It will be negative. So we can just using this inequality take some time to prove, okay? And then this is where the third derivative of x, absolute value, is less equal m. And because x is in between 7 and 9, so we will have, so because x is greater or equal 7, and we have x 8 over 3, so we need to have this inequality. Okay. And so the third derivative, or maybe let me write the third derivative from here. Okay. The third derivative is 5 to 10 over 27. So 10 over 27 x negative 8 over 3. Okay. Or we can have this 7 over 27. And this should be less equal than the minimum x that we have in the interval. Okay, so 1 over 7 8 over 3, which we have calculated that this is equal to less than 0.0021. Okay. So we check some numbers first, okay, from the minimum numbers that we have from the interval. And based on what we have here, then we can assume this m with this number. Okay. So that we have the remainder is always less than those numbers here. So we are having the accuracy in between this 7 and 9. Okay, assuming we take m equal 0.0021. Okay, and then if we look on this statement, we can take this into x minus 8, and then we can simply write that this is true, and then the Taylor inequality gives less equal or this is equal with 0.0021 divided by 6. And thus, the accuracy that we have is less than 0.0004. So if then accuracy is within 0.0004. Okay, one more, I think, example, and then we finish all the chapter 11. What is the maximum error but possible in using approximation of sine x approximate when the interval of x is between negative 0.3 and 0.3. Use this approximation to find sine 12 degree correct to 6 decimals. And the second one, for what values? Following question, for what values of x is this approximation accurate within 0.00005? And for obvious reasons, of course, you might need calculators to check, okay? Because the approximation is usually dealing with errors, and errors is dealing with the decimals, no? in decimals. So first is we are going to see the approximation. We already have the approximations. Of course, this is a function of sine, and then we looking on the t, okay, some t of sine, right? Some partial sum, and then we have the interval for x. And for obvious reason, you see that the interval is really small, okay, 0.3, negative 0.3 to 0.3. So first we find the maximum error. So we find the remainder. Okay, we find the remainder. And the second one, we find the sine 12 degree, okay, using this approximation.
And then the second one, if we change the error to be this accuracy, 0.00005, okay, what will be the x? So that's the key question. So first, maybe we deal with the first one, the A, and then this is the B.
So let me write this as A and this is B. Maybe let me write the Maclaurin for sine to help you also familiar with the Maclaurin series. For sine is the odd number and then factorial and then alternating. Okay. And since it's alternating and it's decreasing, it becomes smaller and smaller, the value, and also the ratio is less than 1. So we can use alternating series estimation. So if we look on the questions, we have
1, 2, 3, 3 terms, right? X cubed, x5, which means in using alternating series estimation, we will just take a look on the 4th term. This is the error. If you remember the previous theorem for estimation theorem. For alternating series, the error will be the n plus 1 for the terms that mentioned. So if the question already take the 3 terms, then the error will be this, okay, x with the power of 7.
So the error at most will have 5040. Then if x is between this, okay, so the error is smaller than, we exchange 0.3 inside and we compute using calculators. I think we can get this, okay, small number. And then to find the sine 12th degree, we can convert this to radian. And then exchange this pi over 15 into our equations, okay, into our approximations. So sine pi over 15 is approximating pi over 15 minus pi over 15 cubed of course you need to use calculators to check this, all these terms. This is correct to 6 decimals. Okay, let me just give you some clue on how we solve B. Okay, so for number B, we start by looking on this error, that the error should be less than 0.00005. So what we are going to do is we need to find the x. Okay, we need to find the x. And you will find the x with power of 7 is less than 0.252, and then we can solve that x is less than, okay?
Okay, probably because there are a lot of how to find the estimations. Each series has its own, sometimes its own estimation. I will mention that when we have some exercise or maybe exam, I will mention which estimation that you should make, so that you will get the correct results.
Okay, any questions? Okay.
So I think this will conclude the chapter 11. If you have time, we will have some review later on, okay, before we have the midterm. And the midterm probably the middle month of April, so after the holiday. And then the next week after that, we might have so before the midterm, maybe the previous week we have maybe some refresh or reviewing material. So I will refresh with all the materials. Okay. So the midterms probably this chapter 10 and 11, okay, because it's already a lot. And next week, since we finished this, and I would just want to go to chapter 12. It's vectors. Okay, so because you already learned before, so I hope we can just take some quick review on vectors and maybe which one is the most essentials in our calculus. Okay, I think that should be conclude our session for today.